Just before dawn, on a cold Sunday morning in December 2005, southern England was shaken by a blast so powerful it registered 2.4 on the Richter scale. People were woken suddenly as houses shook and windows were blown in for miles around. A towering wall of black smoke engulfed the sky, spreading as far as France and visible from space. What followed was one of the worst industrial disasters in the UK. Over 2,000 homes and businesses damaged, air and road travel were disrupted, fires raged for days, and 43 people were injured. Yet miraculously, there were no fatalities. At the heart of Britain's biggest peacetime explosion stood the Buncefield terminal, one of the UK's largest fuel storage sites, and a disaster waiting to happen. Located near the M1 in Hemel Hempstead, Buncefield was the fifth largest fuel distribution terminal in the United Kingdom. It sat at the centre of a network of pipelines carrying petrol, diesel, and aviation fuel from refineries at Lindsey, Stanlow, and Corryton. Fuel was transferred through the network in large batches and was stored in above-ground tanks before being transferred by road tanker or pipeline to stations, airports, and industry across the south of England. At the time, Buncefield supplied almost half of Heathrow Airport's aviation fuel. The busy site operated 24 hours a day, with throughput increasing year on year. At the time of the incident, Buncefield handled fuel through three major pipelines. One of the busiest tanks was Tank 912, capable of holding 6 million litres of petrol.
Tank farms are absolutely essential to the UK economy. They provide an interface between different modes of transport, and that could be things like ships or trucks or pipelines. And they allow for the import of products into the UK, storage of those products, and then the onward export of those products. And many tank farms and terminals are actually what we call multi-product. That means that they don't just store hydrocarbons, things like gasoline, diesel, and jet fuel, but they will also store other substances like chemicals, foodstuffs, agricultural products.
The disaster unfolded gradually. On Saturday, 10th of December, at around 1850, operators began filling tank 912 with unleaded petrol. At around 3 o'clock, the automatic tank gauge froze, flatlining, displaying the same reading, leaving operators blind to the rising level, a recurring problem that had been logged many times in the previous 3 months but never resolved. At 5:20, calculations show that tank 912 was full and beginning to overflow. At 5:38, CCTV captured a vapour cloud creeping across the site, across the bunded area to the northwest corner. The cloud was about 1 metre deep. At 5:46, the vapour cloud thickened to about 2 metres and was spreading in all directions. By 6 o'clock, pumping rates increased to nearly 890 cubic metres per hour as operators, unaware of the overflow, continued receiving fuel. The cloud spread off-site into car parks and between buildings. At 6:01, a worker raised the alarm after noticing fuel spilling, activating the emergency response. This started fire water pumps located within the vapour cloud. Moments later, the cloud found an ignition source, likely the pump or a nearby generator, and exploded. Secondary explosions followed, and a massive fire engulfed over 20 large tanks. The explosion injured 43 people. More than 2,000 residents were evacuated. Over 600 businesses were damaged or destroyed, and the economic shock was felt across the region. Fire burned for 5 days, while teams of firefighters and military personnel tried to tackle the blaze. The problems didn't end there. Bund walls leaked through cracked joints. Pipes ruptured. Firefighting efforts used more than 50 million litres of water. Without tertiary containment, vast quantities of fuel, foam, and firefighting water escaped off-site and into the local watercourse. Environmental monitoring continues to this day. The economic cost is estimated to have exceeded £1 billion, but the emotional impact and the long-term recovery last to this day.
The first layer of protection that effectively failed, physical layer of protection, was the automatic tank gauging system. And the automatic tank gauging system is basically a level gauge on the side of the tank. And the thing about the ATG at Buncefield on that tank is that it was known to be faulty. It was known to stick. and therefore give false results. And there have been several reports that have been put in about it sticking, but nothing had been done to fix it. If we look at the second layer of protection, if you like, as well as the automatic tank gauging system, there was also something called an independent high-level alarm, which is basically a float switch which sits at the top of the tank, which will indicate to the operators on the control system that there's a problem, that the tank is overfilling, and you've got a high-level alarm. The problem with the float switch is that it was engineered and it was installed absolutely correctly, but there wasn't sufficient information passed to the people that had to operate and maintain it about how it should be safely worked. And it actually had a padlock associated with the float switch, which would padlock it and secure it into a normal operating position. And that padlock was applied to a handle. And unfortunately, no one really knew or understood the importance of what that padlock was there to do. And what happened was that the padlock hadn't been reinstalled after a test, and the handle dropped, and that put the float switch into the test position. So it was never going to work. It actually worked as absolutely as it should, but it was inoperable because it was in a test position. So if we look at those two factors, first of all, the operators had no idea how much was actually in that tank, because the automatic tank gauging system was known to be intermittently faulty, and the independent high-level switch was left in a test position, so there was no way to know how much product was in that tank. You also need to look at the remote filling of that tank. So gasoline was coming down a very long pipeline, and actually the Buncefield site had no control over that filling, other than to get onto the phone to the sending site to say, stop your pumps, we're getting full. And that was another failing. There was no way for Buncefield site operators themselves to actually stop that transfer.
This was not just bad luck. Multiple degraded barriers aligned. Repeated automatic tank gauge faults were tolerated. Independent high-level switch replacement was not managed. Bund integrity and tertiary containment was insufficient. Emergency plans did not consider a vapor cloud explosion. Product transfers were controlled off-site with poor means of communication. Leadership engagement in process safety was not sufficient. Poor culture. It's just a tank farm. It's low risk.
If there's one lesson to learn here is don't forget that there are 3 simple things that you need to think about. 1 is what can go wrong. 2 is what measures do you have in place to stop those things going wrong. And number 3, how do you make sure that those measures you have in place are working?